Alright, this is going to be the last section in chapter 5 that we cover. Um, the rest of it is on something called linear programming, which is very interesting stuff. That was a big part of my master's project was studying linear programming and what's called optimization, finding the best solution to a scenario, but it's a little too different from what we're talking about. These concepts are new. We want to get used to just solving systems of equations and writing them as matrices and stuff like that. So 5.3, and then we're going to go to 6.1 and get more into matrices and how do you add them and all that stuff. So we have taken the concept of systems of equations to introduce matrices, right? So if we're given a system of equations, we would write this system, which I haven't completed yet because there's supposed to be stuff on the other side, but the coefficients are what we care about. So I asked last time, last lecture, what's the important stuff, the necessary stuff in order to solve our problem. The only necessary stuff is to write the coefficients. So a11, a12, a21, and a22. And this is our matrix. Really, this is the stuff that we're going to explore. For now, to solve it, we write an augmented matrix if we're given the other side of the equations, K1 and K2, and then over here we'd write K1 and K2. And then we do our row operations. So we have our row operations, which are basically our ways of manipulating systems of equations without changing the solution. So we do the row operations for an augmented matrix are the same as those three rules that we had in Theorem 1 back in section 5.2, I think, for how you can mess with the systems of equations. You can switch the two equations. If I call this 1 and 2, I could switch 1 and 2 and it doesn't change the solution. I can add them together. I can multiply them by constants and it doesn't change anything. So similarly, we have a set of row operations that preserve the solution and doesn't change it. So we can do kind of all those same things to matrices. And here they are again. We can interchange rows. So this would become, and I would write this as row 1 interchange row 2, 2, 4, 1, 3. We can multiply a row by a non-zero constant. So let's say row 2, I multiply it by 2. Then this becomes 1, 3, 4, 8. And then I can add a multiple of one row to any other. Okay? So if I multiply this row by negative 2 plus row 2, remember the row that changes is when you're doing row operation 3, the row that changes is the second one, not the first one. You leave the first one alone. So I'm just going to copy down, or whatever the first written one, not literally row 1. So row 1 is the first one that I wrote, so 1, 3 gets copied down. The second one I wrote in this operation is row 2, so that's the one that changes. So negative 2 times row 1 is going to give me negative 2 plus 2 is 0. Negative 2 times 3 is negative 6 plus 4 gives me negative 2. So these two matrices are row equivalent, these two matrices are row equivalent, these two are. In fact, all these matrices are row equivalent to each other. Yeah, so the solution doesn't change. Um, Important thing to notice is right here I have a 1 and I have a 0. I want to get these. Alright? I'm not necessarily thinking, I've done a lot of linear algebra. It's one of my favorite subjects. It's extremely relevant because it's really elegant math when you get past all this tedious stuff. Um, it's not super advanced math, but it's somewhat up there when you can get deep into it, and it has a lot of applications in the real world. I mean, um, it's hard to say exactly what the percentage is, but anywhere in business or finance or engineering, you're going to have a simultaneous system that at least is going to be approximated by a linear system, and you're going to want to use linear algebra in order to solve that. Um, and you're going to do it with a computer, but if you're in a technical job and you want to have a higher pay, and you're the guy who knows the math behind all that, and you can write the codes and everything, this is what will get you there. So that's enough of that. All right, getting zeros and ones is what we care about. That was what I was trying to say here. You want to get zeros and ones. That's what I'm thinking of. I'm not thinking of, okay, multiply this row by this row. After you do it 100 or 1,000 times, you just like, okay, let me get zeros and ones in each row, move stuff around, and eventually I'll get what is called the reduced row echelon form. So the goal is to take a matrix from here, this form, to here, where I have whatever my constants end up being, and here I'll have 1, 0, 0, 0, 1, 0, 0, 0, 1. So this square matrix, this part is square, the whole thing is augmented, but this part is square. This is in reduced row echelon form. Reduced row echelon form. Okay? And I'm doing this using only row operations. Now the book calls this reduced form. It calls this a reduced matrix. But most other books that I've ever read always call it reduced row echelon form. And there's even a note in the book on page 415 that it's really called reduced row echelon form. And your calculator even has a little feature that we'll learn. I'm going to post a video, or I hope to post a video that shows you how to do all this stuff in the calculator so you don't have to worry about the arithmetic so much. But it says RREF, reduced row echelon form. Okay, so that's the goal, is to get it from here to here. And it's not, this reduced row echelon form won't always look like this. It won't always look like a square matrix with ones right along the diagonal. It has certain properties, because this, I can have a matrix that's more rectangular, like 1, 2, 3, 4, 5, 6. This has a reduced row echelon form, but it won't be ones right along the diagonal. This has no diagonal. It's not square. So there's a set of rules that we have about what reduced row echelon form needs to look like. We can't really represent it with one picture or example like right there. So here's the definition on page 415. A reduced matrix, or reduced row echelon form, has the following properties. 1, each row that consists entirely of zeros is below all other rows, basically. Non-zero rows. Non-zero rows. All right? So if I have something like this, I have all zeros on the bottom. This is potentially in reduced row echelon form. And if I have anything that's non-zero in my other rows, let's say I have like a 1 here, and I have zeros everywhere else, and I have a 2, 4, 5. Okay, this isn't quite reduced row echelon, but um, you know, it could be if I'm just looking here because I'm following this first rule. My 0 row, if I have a 0 row, is going to be at the bottom. That's the best way to say that. If I have down here 1, 0, 0, there's no way that this is going to be in reduced row echelon form. Let me erase that. Forget that top row. This is potentially in reduced row echelon form. This one is no way because it's breaking that first rule. Or if I don't have a square matrix, if I have something like this, this is reduced row echelon form where this is not. Okay? Rule number 2. The leftmost or leading non-zero element in each row is 1. So the leftmost non-zero element in each row is 1. So if I have a row and I have any zeros, they go to the right and my ones go to the left. This should not be a 2. I'm going to divide those out. I'm going to do my row operation number 2, which says I can multiply by a constant. So if this was a 7 to start, I would do a row operation and say, okay, multiply by 1/7 and turn this into a 1. So this would be in reduced row echelon form, whereas this could not be. Because even though my row of zeros is on the bottom, this needs to be on the left of everything else in that row. See, I have a 0 here. This is to the right of this, which isn't going to work. Okay. Or here's another example. This is reduced row echelon form. This is not. So yes, no, yes, no, yes, no, and so on. Number 3, the column containing the leading 1 of a given row has zeros above and below the 1. So any leading 1 has zeros above and below it. Okay? So this is potentially in reduced row echelon form, where this is not. Let's say I have a 3 here, and I have a 0 here, or vice versa. This could be, this is not, because it has to have it has to have zeros above and below the leading 1. Okay? Number 4, the leading 1 is to the right of any leading 1 in the preceding row. So is to the right of any preceding row. Preceding meaning above. So if this is a leading 1 in this row, then it must be to the right of a leading 1 here. Okay? So this is potentially in reduced row echelon form, but this, let's say I have a 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, whatever. This could not be in reduced row echelon form because it's following this rule. See, I have zeros above and below. The leftmost non-zero element is a 1, with these. Actually, that's not true. See, this one's breaking this rule, rule number 2. But it's definitely breaking rule number 4. This is to the left. of this, which it should not be. So this is not reduced for echelon form. So why don't you just give me a picture, as I said before, um, and I'm trying to illustrate with these examples that there's many different types of matrices. They're not all square or 3 by 4 or something like that. There's many different types, and so we have to state reduced row echelon form as a set of rules, rather than just like I showed you the general form of a polynomial function. We don't really have a general picture of what reduced row echelon form would look like. Maybe we could write one, but it's better just to write it as a set of rules. So, okay, what's the point? What's the point of this reduced row echelon form? Why are you making my life difficult? Well, when you get a matrix in reduced row echelon form, we have the solution to our linear system. Okay? So as an example, 1001, let's say this is 317. Okay, this is in reduced row echelon form. So this is a solution of my system, where this row represents my x value, and this row represents my y values. X is equal to 3, y is equal to 17. And I have an extra row of zeros here, which is not even being used, but that's why we do it, because that means we're solving the system, and once we get into that form, it's obvious that the solution is just whatever's on the right hand side. Now, how do we get into reduced row echelon form? Well, this is something called the method of how you do this is called Gauss-Jordan elimination, and this is on page 417. Gauss is considered by many to be the greatest mathematician of all time. He's the king of mathematicians. There's all these ways of praising him and talking about how smart he was, and he was very smart. There's stories of him being 5 or 6 years old. I think I told one at the beginning of the year of where he solved this, very cleverly solved this problem that his teacher gave the class for busy work. So, and then if you study a lot of math, you'll realize there's always Gauss this, Gauss that. He's everywhere, along with a few other big names. Jordan was a guy who generalized Gauss's work. So when something like that happens, you want to give both guys credit. So we have Gauss-Jordan elimination for this procedure. Whoop-de-doo. Okay, so now the idea is you're given a system of equations, and you have you write the coefficients, as we know, because that's really the only important information to solve it. So there we have our matrix now, our augmented matrix, and we want to do these steps to get it into eventually reduced row echelon form. So we want to have these little goals, right? That's what I'm trying to say here. We want to have first. This is our first goal: is to just get a 1 in the top, or get a 1 somewhere. Just give me a 1, give me a 0. Just start getting them, and you'll realize that the solution will start to come out. Because right now this just looks like a mess. It just looks like a mess of numbers. So that's how what this is trying to do. It's trying to give you a set of small little goals to get to, getting 1s and 0s, and getting them in these particular spots, and then the solution will come out. So the best way to learn it is to do it. Example 3, page 418. We want to solve this system, and so we start by writing the coefficients. 2, -4, 1, vertical bar, -4, 4, -8, 7, 2, -2, 4, -3, 5. Okay, right? So, what do I do now? Well, I can multiply the first row by a half. So I will do that, right? And look, I have a goal that I just met right there. And then everything else just gets copied down. You'll find it pretty irritating to have to keep rewriting and rewriting and rewriting, but it gets better. Okay, we can do a couple things here. We can add -4 row 1 plus row 2, and we can also add twice row 1 plus to row 3. Okay, let's do that. So we have, that gives us 1, -2, and 1/2, because remember, we don't change row 1 if we change the second thing that we write. And then we have here 0, 0, 0, 0. And then, so we got a bunch of zeros, you see? And then 1, -2, vertical bar, and then this all changed to 1/2. I'm sorry, this is 5. 5, -2. And then this is -2, 10, and 1. Okay? Then we can multiply the second row by 2/10. So 2 over 10 times row 2. Everything else just gets copied down. And we get 0, 0, 1. And then this becomes 2. 0, 0, -2, 1. Okay. And then finally, we can multiply the second row by 2. So you see we have a part of our solution right here already that showed up. And then add that to row 3. Why did we do that? Because we want to get a 0 here. The goal is to get 1s and 0s. 1s on the top rows and 0s on the bottom rows, or 1s, yeah, you want 1s on the left if you're on the top upper rows, and then as you go down you want your 1s to be on the right. So then we have 1, -2, 1/2, and -2, 0, 0, 1, 2, 0, 0, and then 2 times row 2, so that's going to make this a 2. Add it to row 3 makes this a 0, makes this a 5. Alright, so what's our solution? Well, our solution is that there's no solution. So I shouldn't have been saying that there's a solution, because you got to wait till the end. And since this is saying zero equals 5, that makes no sense. So no solution. Alright, so you stop here. This is not yet, notice that it's not yet in reduced row echelon form. So they're making a point with this example that you don't have to do the whole thing, because if you get something like this, if you get this contradiction, you don't have to do the whole thing. So if you get a contradiction, stop. Don't make life worse than it has to be. Just the problem is done. All right. Let's do example 4. Let's see if this one actually has a unique solution or not. It does. Okay. Or it actually has a lot of solutions. Okay. So we do this. We do 3 6, negative 9, vertical bar, 15, 2, 4, negative 6, 10, negative 2, negative 3, 4, negative 6. Alright, and we start doing our steps. And that's the trickiest part is figuring out what step to do, or more like once you do the step, the arithmetic of it, like I've been saying. So you could do anything you want as long as you're following those row operation rules. You don't have to do it the way I'm doing it here on the paper. There might be a faster, better way. So let's do 1/3 row 1, 1/3 row 1. Okay, and let's see what we get. We get 1, 2, negative 3, vertical bar, 5. And we get excited because we have a 1 here, you see? 2, 4, negative 6, 10, negative 2, negative 3, 4, negative 6. And then let's multiply the first row by negative 2 and add it to the second row and see what we get. So something doesn't change. This doesn't change. So we just copy it down. The third row doesn't change. It's not even in this operation. So we just copy that down. Whoops, negative 2, negative 3, 4, negative 6. And then this operation gives us zeros all along the second row. Perfect. Okay. So now we can go ahead and switch well, also let's do another step before we do that. Let's do 2 times row 1 plus row 3. So row 1 doesn't change. This is all zeros. And then row 3 becomes 0, 1, negative 2, and then 4. And now let's go ahead and switch because we're allowed to. Rows 2 and 3. So that becomes 1, 2, negative 3, vertical bar, 5. Why do we switch? Because any row of zeros has to be on the bottom. So 0, 0, 0, 0. And then 0, 1, negative 2, and 4. Okay? We're not yet in reduced row echelon form for one reason, and that's we have a 2 here that we need to get rid of, because any leading one has to have only zeros above and below it. So this is a leading 1. It's the leftmost one in that row. So we have one more step. We'll do negative 2 times row 2 plus row 1. And the reason we want zeros is because once we have them, you see, I don't even have to think about it. First of all, the second row doesn't change. Neither does the third. But I don't have to think about what's going to happen with this element here, because 0 times anything is 0, so this doesn't change. Here this becomes a 0 because it's negative 2 times 1 plus 2 gives me 0. And then this is going to become a 1, and then this becomes a negative 3, right? So, conceptual question before I give it away, does this have a solution? The answer is yes. Not only does it have a solution, it has infinite solutions because I have a row of zeros and I have no contradictions anywhere. So, infinite solutions. And I think eventually, maybe in chapter 6, we'll write x1 plus 0x2 plus x3 equals negative 3 for our first row, 0x1 plus x2 minus 2x3 for our second row, and then 0, da 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 da. And then what we can do is we can solve this for x2. So here we would get x2 is equal to 4 plus 2x3. And then here we would get x1 is equal to negative 3 minus x3. So you would write a vector as, so this is your free variable. This is your t that I kind of talked about last time. And this would become -3 minus t for your first element. 4 plus 2t for your second element, and then just t for your first element, for your third element. So you have infinite solutions as long as they are points that are on this line. This is a line in 3D space. That's off the origin, so I'm not sure exactly where it is. I just know it's not on the origin, so it's something like that maybe. As long as there are points on that line, that solves this. This is the intersection of planes. This is two planes, I guess, that are intersecting, and when they overlap, they make a line. So that's what that is. All right. So that's pretty much it. Is the for section 5.3 is you want to just get in the habit of doing this procedure over and over again, getting ones and zeros everywhere, getting into that form, and then saying, what's my solution? This last part here, don't let that freak you out. The book isn't asking you for that yet. I'm not going to ask you for that yet. I'm just kind of foreshadowing. So really what you want to be able to do is all of this stuff up here. You want to be able to do all of this. Get to here. Okay, don't worry about this kind of theoretical stuff over here yet. Get to here, and then I'll be satisfied. So I'll do a couple from the homework, but they are kind of repetitive, and I'll be mindful of that when I assign you homework. So let's say number 1. So if a matrix is in reduced form, say so. If not, explain why and indicate the row operations necessary to transform it into reduced form. So most of these are going to be either 1 or 2 steps away so that it's obvious. They're just trying to get you used to what reduced form needs to look like and how to get it there, with some simple steps. Excuse me. Is this in reduced form? Well, I check. Are all of my ones to the left of any zeros in that row? Check. Is all my ones have zeros above and below? Yes. So I go through the list and I realize this is reduced form. Really, again, it's called reduced row echelon form, but this book calls it reduced form. Number 3. So that we have 1, 0, 3, 0, 0, 0, 0, 1, -1, vertical bar, 2, 0, 5. Is this in reduced form? No. I have a 1 here. This is my leading one. But I have a row of zeros here that's not in the bottom. So my step would be changing row 3 with row 2. And then I would get 1, 0, 3, vertical bar 2, 0, 1, -1, 5, and 0, 0, 0, 0. And this would be reduced row echelon form here. So at that point it is. I'll do let's see, number 9. Is this non-square matrix 1, 0, -3, 0, 1, 0, 0, 0, 1, 1? Is this reduced row echelon form? No, because of this right here. I need a 0 up here. So I can take 3 times row 2 and add it to row 1. And then row 2 is not going to change. So then I'll have 1, 0, and then this becomes 0, 3, and this becomes 1. Okay? Might be tempting to say it's still not in reduced row echelon form because of this, but this is not a leading 1. So this is checked. This is reduced row echelon form, or again, the book calls it reduced form. Okay. In problems 11 through 18, they're trying to get you to think of consistent, independent, inconsistent, all that stuff. That just means do I have one solution, infinite solutions, or no solution? It's that type of talk. So if you have a matrix that has infinite solutions, that is a dependent system, because what it means is one of your rows, so actually let's start with number 13. 1, 0, negative 2, 3, 0, 1, 1, negative 5, 0, 0, 0, 0. So let's say this started from some other linear system, linear matrix, and I did my reduced row echeloning stuff, my Gauss-Jordan elimination, and I got to here. What that means is that this third equation was a linear combination. It was some row operation of the first two rows. So when that happens, you get all zeros. And since it was row operations of row 1 and row 2, we say it's linearly dependent. Row 3 is linearly dependent on the first two, meaning we say it's a linear combination of the first two rows. Okay? Number 11, I'm sorry, so this would be a consistent, meaning there's no contradiction, there is a solution, we have infinitely many solutions actually, and it's linearly dependent. Since we have infinitely many solutions, it must be linearly dependent. Alright, so number 11, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Once you see this, the identity matrix, if you have a square matrix and you see the identity, it basically means you have a unique solution. I'm pretty confident that that's the case. So this is a consistent system. There's no contradictions. I have 1 is equal to 0. Not really. I have 1 times x3 is equal to 0. So that just means my third, whatever my solution is, my x, whatever that vector is, I have to have 0 in the third entry. I have to have 0 right there. That's all that means. So it's if I had the other way around, then I'd have an issue. So 0, 1, bad. This is okay. 1, 1, 1, 1, and a 0 over there, that's fine. So this is a consistent, independent system. Independent. Okay? So that's what that means. The thing to look for is a row of zeros. If I have a row of zeros, it's dependent. If I don't have a row of zeros, it's independent. If I have a contradiction, remember, if I have something like 0 equals 7, if I have a contradiction, that is an inconsistent system. Okay? Let's keep going. Number 19. So we have 1, 0, 2, 1, negative 1, 3. And it says use row operations to change each matrix to reduce form or reduce row echelon form. So this one, these are very nice. They're one step away. All I have to do is multiply the second row by 2 and add it to the first row. So I do not change the second row when I copy it down. The first row gets changed. This doesn't, nothing happens because that's a 0. And then this becomes a 0. And then negative 2 times 3 is negative 6, plus negative 1 is negative 7. So that tells me this is reduced row echelon form. More importantly, I know my solution is x is equal to negative 7 and y is equal to 3. But that's not what they're asking for. Just that's the point of all of this. Let's see. Number 21. 1, 0, negative 3, 0, 1, 2, 0, 0, 3, vertical bar, 1, 0, negative 6. So, this is not quite in reduced row echelon form. There's a couple steps needed here. If I divide the third row by 3, oops, 1/3, sorry, 1/3 row 3. So everything else just gets copied down. This becomes a 1, which we like. Okay. Another step. I don't want to. I can't have a anything above my leading 1 for this row. So I'll do 2 steps in one. I'll take row 3. I'll multiply it by negative 2 and add it to row 2. Then I'll multiply row 3 in the other step by 3 and I'll add it to row 1. So row 3 is not changing. But row 2, because I'm multiplying this by negative 2, that makes this, whoops, that makes this a 0, and that makes this a 4. And then row 1, this becomes a 0, see, because 3 times row 3, 3 times everything in row 3, 3 times 0 is 0, added to 1 just leaves it the same. 3 times this number, when I get to that number, is 3. Added to the negative 3 gives me a 0, so that's what I write there. 3 times the negative 2 is negative 6, plus 1 gives me negative 5. So this is reduced row echelon form. My solution is x is equal to negative 5, y is equal to 4, and z is equal to negative 2. Otherwise written as x, the vector, is equal to negative 5, 4, negative 2. I have a unique solution at one point, or one vector. All right, that is the end of 5.3. Again, I'll post the homework when I think of exactly which problems I want you to do, but it'll be at least through like 44-ish, maybe a little bit more.